Hi everyone, my name is Mike and I have 10 techniques that I'm sharing for making group delay measurements on frequency converting devices that have embedded local oscillators. For example, devices like this Mytek satellite block down converter, which takes a 20 gigahertz input signal, mixes it with an 18.75 gigahertz LO, and puts out an IF signal at about 1 gigahertz. So a device like this with an embedded LO, I want to measure the group delay of this, and I have 10 techniques that can be used to make the measurements as fast, as easy, and as accurate as possible. So, for making a measurement like this, of course, I'm going to use the Rohde Schwarz ZNA vector network analyzer, which we introduced to the market about 1 year ago. This instrument has been optimized for making frequency converting measurements like this. And in particular, I'm going to use option K9, which is our two-tone technique for measuring group delay on devices with embedded LOs. Now, if you want more information on this technique, we have an application note, 1EZ81, which goes through all the details of making group delay measurements on frequency converting devices. But I'm making some videos where I share with you in each video one of my ideas for making the measurements more accurate. Okay, so in this series of videos, I have 10 ideas, and in this particular video, we are going to go through idea number 8, which is use 2 internal local oscillators on the network analyzer to make the measurement of your frequency converting group delay. Now, in order to understand what that means, we have to take a quick look at the block diagram. But we have an option in the Rohde Schwarz ZNA network analyzer to install either one local oscillator, which can be shared among all of the receive ports, or we can install 2 local oscillators. Now, the advantage when we install 2 local oscillators is that the port 1 local oscillator can be committed to looking at the RF signal that's going to the device under test, and the port 2 local oscillator can be committed to looking at the signal coming out of the IF of the device under test, which is obviously at a different frequency. The advantage when we use 2 local oscillators to stare at the RF and the IF at the same time is that the measurement is twice as fast, but also the measurement is more accurate because there's no chance for phase drift to occur between when we measure the input signal and when we measure the output signal. So in this video, what I'm going to do is create 2 channels, and I'm going to calibrate both channels exactly the same way, but in one channel, I'm going to use 2 local oscillators to make the measurement, and in the other channel, I'm only going to use 1 local oscillator. That way we can directly see the impact on the measurement results right away. This will help you decide whether or not it's worth buying that second local oscillator, which is option B5. So let's get right to it. We'll start from a preset condition on the instrument. I'm going to launch that GPIB Command Explorer tool like this, and I'm going to make it full screen in this second window. And then I'm going to run the script that it created, which will make these 2 channels that we want to measure. So I'm in idea number 8, use 2 internal LOs. This will set up the channels. It asks me to connect the calibration mixer, which I've already done, and it's going to calibrate the 2 channels. Now that it's done with that, we have 2 channels, and in the first channel, I'm only using 1 internal local oscillator for the measurement, and in the second channel, I'm using 2 internal local oscillators. So where do we enable this option? Well, it's under the mode key, and this is where we can select using 1 or both local oscillators if the option is installed in the instrument. Now I want to point out, if you have 2 local oscillators, then the instrument's going to use both of them by default. It's going to pick the optimal setting by default. So you always get advantage of the 2 oscillators if you have them installed. But the reason for us to look at it today is to compare what happens if I don't have 2 oscillators compared to when I do. So how much of an improvement does it give us? Now also keep in mind, this is idea number 8 on my list. That means I've already implemented the first 7 ideas, and we're taking advantage of all of them, which is automate the measurements so I don't forget any settings, optimize the power levels for both my receiver and my transmit signal coming out of the network analyzer, optimize the tone spacing, optimize the resolution bandwidth, pick the best averaging possible, and so on. I'm already forgetting what all the ideas were, but I'm taking advantage of all these things already, so my traces are looking really good right now before I even take advantage of the 2 internal local oscillators. But let's take a look now at what it looks like. So what I want to do is couple these 2 traces so they have the same scale. So I go to scale coupling, couple them both, and then I can move them around, and maybe we zoom in just a little bit to see what the noise looks like on these 2 traces. So now I can see when I have 1 local oscillator, my peak-to-peak variation is on the order of 500 picoseconds on the trace, whereas when I use 2 local oscillators, My peak-to-peak variation is on the order of 50 picoseconds. So this is an order of magnitude difference in trace noise just from using two local oscillators. The other thing you want to notice is the sweep speed. So this top trace using one oscillator takes twice as long to sweep because that oscillator must be tuned to the RF frequency and then the IF frequency for each measurement point. So it's going back and forth twice as often. On the bottom channel, where I have two local oscillators, I'm staring at the RF and the IF frequency at the same time, so the measurement can be twice as fast. So not only is the trace noise much lower by an order of magnitude, but the measurement speed is twice as fast. So this is a very valuable option from that point of view. Now, I have 10 techniques for improving your group delay measurement. This is idea number 8, and it shows the advantage of two local oscillators inside the Rohde Schwarz ZNA network analyzer. Now, I wonder what idea number 9 is going to be. These traces are getting really clean. How much further can we go? I don't know, but we're going to find out. See you then.